All right, so thanks everybody for joining. I was asked to introduce myself. um, so I'm Teresa Vidal Calleja. I'm program co-lead of Program 1, which is in Biomimic Cobots and the Australian Cobotics Center. I'm also the research director at the Robotics Institute in UTS and acting health school of the mechanical and mechatronics engineering. So, all right, so thanks guys for joining. Today I'm gonna talk about our work on empowering robots with continuous and space and time representations. And this presentation is based on a keynote I gave in the International Robotics Conference on in IROS last year, at the end of last year. And obviously I have to apologize in advance because this presentation was designed for robotics researchers. But I tried to I tried to make it more for general audience. Bear with me, there will be some technical things that I will be talking about, but hopefully you can all follow me, and especially people who are not in robotics. I'll be happy. Feel free to interrupt me. I won't be checking the chat or even the hands up or things like that. So feel free, just unmute and ask questions if something. If I said an acronym that you don't understand, robotics is my understanding, but other people might not have it that clear. Yeah. So hopefully it will make sense at the end. And I must say, I'm going to a little bit of some fundamental aspects, some more theory-based initial part. Just bear with me. After there will be some nice videos. So, cool. All right. So let's go. Yes, now this is working. All right. So in robotics, most of our representations for localization, mapping, and planning, which is the key essential capabilities that a robot needs, especially when doing autonomous tasks, are mostly discrete, right? So in time and in space. So in time is when we localize our robot over time. So we find the position of that robot, the position and orientation of that robot over time. And we usually do this with state estimation algorithms that require that we, at given discrete times, like here, like this is, imagine a mobile robot moving from time through the space. And in the state estimation, we usually have the position of this robot at discrete timestamps. And we also observe, like there hasn't been many representations of the environment proposed over time, but we also have this discrete, usually discrete representation of the environment. So in the simplest case, it could be 2D points, 3D points, but they are not very representative. And there have been many works on this, on a problem of doing this simultaneously, which is called the SLAM problem, the simultaneous localization and mapping problem, which is a lot of my work is, especially early in my career, a lot of my work was focusing on this problem, but I still like it and I'm still working on it for different aspects. Anyway, so this is all discrete. Also, we have these mapping representations. So how do we represent the environment better than just simple points, right? They are also discrete. If we do something more dense, we normally, in the simplest form, we discretize our world. Let's say in 2D, we want a robot to navigate on a room. We discretize our world in 2D. and then we classify each of these little cells of our grid in whether it's occupied because it has been observed by a sensor, right? Like for instance, a laser rate finder that return points on the surface. So it will say it's classified as occupied or unoccupied, or maybe unknown because we haven't explored it yet, right? So it's all very discrete. And there are extensions like very well-known work called Octomap of this type of representation, but in 3D. So you can see for manipulators and for cobots, it's 3D representations of the environment makes more sense. So we have that extension called Octomaps for this discrete representation of occupancy maps, that it's called. And yeah, more recently, something more on distance field has been introduced. So what does it mean? So we have other dense representations that allows us to decide whether the distance to the object what's the distance to the object? So representing a bit more the free space, right? And again, this is all discretized. So we put distance associated to a little grid and things like that. And that's commonly known. So for people who in robotics, I don't know, the typical TSDF that allows us to know closer, if you're closer to the surface, if you're on the surface or far away from the surface. Okay, so this is how we represent the world and the state of a robot in robotics. So my my argument on this talk is that we should ditch discrete representations. Why do we focus on continuous representations, right? So despite our sensors are producing discrete data, and of course our robots reason in discrete processing units, our real world is continuous, right? It's not divided in little cells and chunks. So continuous representations in general can provide robustness and more flexibility to deal with temporal dependencies and synchronization between sensors. It's more natural for interaction, like human-robot interaction or navigation in changing environments, and for forecasting potentially when we don't know exactly what's happening, but we need to find a model, right, that tells us a little bit about the future. And yeah, so that's now I'm going to talk about how do we approach this idea of using continuous representations for robots. So this presentation will be divided in 3 main lines of work of my group related to continuous time, continuous space, and continuous time and space representations. First, well, I'll mention in continuous time, we mainly gonna focus on inertial aided systems, and I'll explain what it makes sense there. And when I talk to continuous space representation, it's more about fields, the distance fields and even, well, implicit surface. Well, we'll talk about that a bit later. And then the continuous time representation that we use for navigation in crowds. Sorry, yeah, cool. All right, so this is where it comes, the little theory first. All right, so let's talk about continuous representations. What do I mean with continuous representations? Essentially, I mean nonlinear functions, right? So instead of having discrete noisy points, so this is essentially what comes from this type of data is what comes from our sensors, right? Or in the case when we are estimating location of a robot over time, that we will have these discrete time locations. So what we want to do with a continuous representation is essentially to fit a function. And these functions are usually nonlinear because, I mean, if everything was straight, well, you can fit lines and everybody knows how to do that. But we want to fit nonlinear functions where we don't necessarily know the level of nonlinearity, right? So we don't want to fit square functions or cubic functions. We want to fit a function that we don't know exactly how it looks like. And we also want to have some level of uncertainty. So that in robotics, it's very important that we reason with uncertainty. What do I mean with uncertainty? How confident we are on that estimation, right? So essentially, we are estimating things because our sensors produce noisy observations. So if you have a sensor that always gives you the same answer, if you point to the same place every time, well, you have the yeah, you hit the jackpot because it doesn't exist or it's very expensive. So usually our sensors are very noisy. Well, not very, some are less noisy, but they usually come with some uncertainty associated. So they always have this, yeah, you have to average measurements to be sure of what the sensor is telling you. So we want this type of representations to help us to capture those uncertainties. And there are many ways the community have solved these non-regression problems using parametric functions, splines, neural networks, Gaussian process. So there are many ways. The way we've been working, the type of representation that I've been working for many, many years, and now most of my PhD students have something to do with this type of representation. It's what we call Gaussian process. And we don't need to understand exactly what a Gaussian process is, but it's essentially, if you are familiar with Gaussian distribution, well, it's the generalization of a Gaussian distribution over a function space, yeah? So instead of being a point and you can describe the Gaussian, the bell curve over a point, you can now have functions and they could be multidimensional. The beauty of these representations is allows us to fit functions without needing to know the level of nonlinearity, right? The only thing that we need to choose is a kernel, so it's a kernel method. Don't worry about it if you don't know what is this kernel method, but it's essentially you pick this type of kernel to make your function more smooth or less smooth. But that's it, right? You don't need parameters. You don't need to decide how, yeah, if it's cubic, quadratic, or logarithmic or something like that. It's only based on the data, right? So it uses the data itself. So it's a data-driven approach. It's probabilistic and allows us also to do operations over it. So despite we don't have a full expression like x squared plus 2, and for instance, if you have a explicit expression for a function, right? Let's say x squared plus 2, you can differentiate that function, you can integrate that function. Well, with Gaussian processes, we can also do that. It's not explicit, it's through the kernel, but we can have analytical differentiation, analytical integration. So all this is something that we are exploiting in this work. So hopefully, yeah, so that's what I was saying. So we can fit a function, which is a Gaussian process. It gives us, it can give us predictions at a continuous level. It can give us uncertainty for when we fit our data, and we can differentiate, we can integrate, we can apply linear operations, and it remains a Gaussian process. All right, so how do we, all right, that's it. I'm not gonna bother you more with more technicalities. Well, a little bit more, but I'm gonna show you how we use these powerful tools. So for continuous time, right? And especially focusing on inertial-aided systems. With inertial-aided systems, I mean, when we have the inertial-aided system, usually we have an IMU, which is an inertial measurement unit, which has a gyroscope and an accelerometer, and we have another sensor, right? So for instance, a camera, like in this video, where you can have an IMU, this is showing the gyroscope. You could have a camera, or you could have a 3D LiDAR, or other sensors like event-based camera, as I will show something in a bit later. So in this case, the way having multiple sensors is also very challenging, right? Because their sensors live in their own world. They don't talk to each other, right? So we have to make sense of all these measurements. So we have sensor measurements of an IMU over time at discrete time intervals, let's say 100 hertz, right? Very common. So these are the timestamps where we get this information. Then, for instance, for a camera, usually our algorithms, our camera, typical camera that we use in robotics will be 30 frames per second. But usually we don't use that much of images. Potentially we have images at less frames per second. So what we call keyframes. So, and they will come at a different timestamp, potentially constant, but a different timestamp. For instance, and LiDARs will come, they can come. So something that it's interesting is how a LiDAR operates. It scans, well, the typical LiDARs, the ones that you see in the self-driving cars, it's a scanner, right? So it scans the environment in a radial direction, right? So if you're moving fast, the first point of your scan, at this point, it might not coincide with the last point of your scan. So it can cause motion distortion, depends on how much you move. So that, I don't know, that also you could take a scan, the timestamps of the scan, or you could also consider every point independently if you want to remove this motion distortion. And there are other type of sensors like event-based cameras that it's a new type of camera. I'm not going to get too much into it because we will run out of time talking about event-based cameras, but it's a kind of a novel type of sensor that produces events, asynchronous events of changes in intensity, right? So imagine a camera where something changes, it produces an event. And these events are completely asynchronous, right? So that's even, if you want to fuse it with an IMU, that's even more challenging because that the times are even non-constant. So it's a mess. All right, so how do we do IMU integration and pre-integration? So IMU gives us, unfortunately, IMU, they are great, but instead of giving us positions or angular positions, they give us accelerations and angular velocities. So that means we need to integrate these measurements to be able to localize our vehicles with IMUs. And there is a common, I mean, something that was seminal work that was published almost 10 years ago, no, more than 10 years ago, about something that is called pre-integration, which allows us to summarize information of IMU for in between the frames of our other sensor, right? So we can summarize all the measurements. Sorry, the light goes off. All the measurements in between timestamps of the IMU, and this and also allows us to decouple from the orientation. That's a technicality, but this is very useful because we can integrate in chunks without having to re-estimate the orientation every time it changes. So, and thanks to this pre-integrated measurements, it allows us to fuse data from these asynchronous sensors in a single timestamp. So what we propose in our work is to do continuous pre-integration, right? So instead of having these discrete pre-integrated measurements, we want to use our continuous functions to be able to have continuous pre-integration over the different times. So fusion is seamless. We don't need to we don't have this discrete idea. We can do it all asynchronously, and it has also uncertainty that allows us to do data fusion, right? And the beauty of what I mentioned before with our functions is that we can integrate analytically. We can integrate our continuous measurements, which in this case, it allows us also to do data fusion in a better way. So the way we call our continuous measurements or continuous pre-integrated measurements is a unified Gaussian pre-integrated measurements. And let's not get into why they unify. Well, they're in this case they are unified because we managed to do the position and orientation together. But those details, we'll leave them for another time. All right, so how do we use it all together to do, for instance, LiDAR inertial integration, right? So in this case, we have an IMU and a 3D LiDAR, and we are able to use this continuous pre-integrated measurement to remove the motion distortion. And what that produces, and integrated everything in a full estimation framework that allows us to do simultaneous localization and mapping and even auto calibration between the two sensors. So because we need to find the relative transformation between the two sensors in any environment, in indoors, outdoors. And the result is that our maps at the end are very crisp because we remove all the distortions. You can see this is just outside my office, and we have a super crisp point cloud as out of the fusion between the two sensors, right? And this is an outdoor example. This is the Koblenz data set where we can see also we get really crisp, no double surfaces, beautiful ground. Despite this sensor is mounted in a car moving fast, right? All right, cool. So we do something similar with this new type of sensors that I was mentioning about, these asynchronous sensors that give us this change of intensity. They are very challenging because it's hard to make sense of all this asynchronous data, right? So every time a pixel intensity change, this camera, which is, well, you can see it here, it gives us an event, right? And all these events, they come like in a stream of space and time. So understanding and processing the data it's quite challenging. But the way we do it is one of these asynchronous events, we are able to associate a pre-integrated measurement, kind of giving a position to all of these events. And that allows us also to undistort as well the events, right? Because at the end of the day, with these event-based cameras, one of the challenges is to project all the events to a single time to be able to see something like an image. So we combine our continuous integrated measurements together with the events to do it again, simultaneous localization and mapping with event-based cameras. All right, this is a slightly different approach. It has nothing, it's not about the SLAM integration. This is about how to decide where to move next, right? So when you're trying to improve your measurements, your estimation, you could also use optimization, or you can also use what we call active perception to forecast where is the best place to go next to have a better localization, right? And you can see you can formulate an optimization that allows us to do this, right? In this case, we have a camera and an IMU system. And what we want to do is to forecast where we're gonna go next to improve our localization. But because we have an IMU, what we need to forecast is it's integrated, or the measurements of the IMU, which is acceleration and angular velocity. So that will give us, for that, we are using our continuous pre-integrated, our continuous function. So we can, because we have positions, we can find that we can differentiate, we can fit a function in position and then differentiate to get angular velocities and linear and linear accelerations, velocities and acceleration. So this is a different use for this type of representation. Okay, and I'm gonna move quickly to continuous space because time is ticking and I'm talking too much. All right, so continuous space. All right, I'm gonna go into another technical explanation here. So the way we do 3D reconstruction, if we want to reconstruct the surface, one way could be just with occupancy, but we move a little bit away from it. The other way is to do implicit surface. And what is an implicit surface? It's essentially in, let's say, in discrete space, you can see, you can have a distance function, right? So if you're closer to the surface, your distance becomes smaller. If you are outside the surface, it's positive. If you are inside the surface, it's negative. So you have this implicit way to describe the surface, and where your surface would lie exactly at the zero crossing. But you are describing your space with distance, right? And this is very well utilized in computer graphics, this implicit representation. So there are many methods to, after you have the implicit surface, you can recover the surface using marching cubes or something like that. So what we propose to use is instead, again, fitting a function to this distance. And because we can also differentiate the function, we can have also the normals, right? And because we have a function, we can also fill data gaps and things like that. So the way we have utilized it, and hopefully this is more appealing for the Cobotic people, we can utilize it to do 3D reconstruction of surfaces of the objects that we are planning to manipulate or the human is going to collaborate with. And these representations are quite, we have implementations that are quite efficient, so we can do this online. Let me just remove the laser pointer because otherwise I cannot click in other videos. But the beauty, what we developed is a framework where we can do this at small scale, but also a big scale. So in this case, we are mapping a cave. I think it's the Jenolan cave data set. So if somebody has been in Jenolan caves, this is one of the caves data is how, that's the surface reconstructed of this data. And yeah, we can do this big data set. So, all right, so moving on, we have also used, we have some work where we use this exact representation to do manipulation, right? So as I was saying, well, if you can reconstruct the surface, you can interact with the surface, right? So you can start moving boxes, decide, you can do exploration, right? You can see where you're missing, where your uncertainty is big because you're missing data. So the active that you can guide your robot to go to those uncertain places to do more reconstruction. And you can, obviously, the information on the surface could help us to decide what box to pick and things like that. And I mean, we did this in simulation, but we also have, we also tested with a real robot, grabbing boxes with a magnetic sensor. All right, so that was surfaces, but now I'm going to talk about fields, and this is one of our very recent work on distance field, continuous distance field mapping. I'm probably not going to get into too much detail here, more going to show you. So now, instead of mapping just near the surface and having a distance field, now we have a way to recover the full distance field over the whole space that we are mapping. And this is continuous, right? So instead of being only close to the surface, we can know everything around in the whole space. And you can see this, how this could be very, very good, not only for surface reconstruction, but also for navigation. And that's how we utilize it. So in this case, we have a camera moving around, and it's mapping the distance field in a continuous manner. And also, you can recover the surface after you have the full distance field. And how do we use this? We can use it for navigating in the safest spot, right? Like, so you can send your robot as farthest away as possible from the surface. You can see how this could be excellent for human-robot collaboration, which is the recent work that we did with our visitors from Germany, from THWS, where we do this distance field mapping in a very fast way. We recover the distance to the gradients as well, because we can differentiate this field, and it allows us to find the hot spots, like where the robot shouldn't go, right? Like if there is a hand, you don't want to do there, and it's fast enough, and we have a way so we can also deal with dynamic scenes, with dynamic objects, and still clear. So that allows this human-robot collaboration more efficiently. And of course, we can design a planner that plans its path in the safest way, while there are dynamic objects in the scene. All right, so this is very quickly, I'm almost done with this. We have some work with the University of Bonn, where we use this continuous distance field to map field, like green fields. And we, in this case, we are able to do it in a more efficient way through multi-resolution. But also that allows us to have planners that can focus on certain areas of the environment, and this is for agriculture applications. And similarly, we have some work with DLR where we have done terrain mapping, and we use the gradient of the terrain to relocalize the robot in this type of planetary-like environments where, like, you can see an autonomous cars are able to relocalize in the cities and things like that, even when they don't have GPS measurements. But for the case of planetary-like environment, is very challenging. So we have to develop specific algorithms where, like, there is no key features you will focus on. It will be just these little rocks, big rocks. So it's the terrain which gives us that highlight. And these continuous fields have proven to be good for doing these localization algorithms. All right, I'm just gonna finish with this quick work that we did in continuous space representation for navigating in crowds, right? So the way we do it is we don't represent crowds as single people, but more in density and velocity fields in the area, right? So we summarize the information of all these people in the area. And you can see in the first part of our work was very discrete. But as I said, with our tools, we managed to have these continuous fields, not only in space, but also in time. And that allows us to do navigation, being able to navigate in that safest area of our field that it goes in time and space. So you can see how all these, the same kind of approach interconnect very different problems. All right, so I'm gonna finish there, and hopefully I managed to convince you that continuous time and space representations are very useful for fusion data, especially when it's asynchronous, that it's very good as for distance field and field in general applications where we can do localization mapping and planning, and that can be integrated nicely also for continuous and space problems where, for instance, navigating in crowds. And just want to acknowledge my PhD students and postdocs who have working with these representations. You can see our good old Fred here, who worked with the TWH guys and on the human-robot interaction aspects, and he also worked with Michelle in the active perception work, and our collaborators in DLR, ETH, BON, and TWS. All right, that's it. Thank you. And I think I'm nearly running out of time, but hopefully there is some time for some questions. All right, I can't hear anything. All right. So if anybody has some questions, feel free to speak up, because otherwise I'll have to.
Yeah, so don't hear. Can you hear me?
Yes. Hi, sure.
Well, one question for the Gaussian process implicit surface.
Yes.
I just wonder if the surface is continuous but not smooth, like a cubic or like those kind of thing. They have relatively sharp edges. Is implicit surface still a good way to do that, or?
Yeah, I mean, the implicit surface has no problem with that, because it's, I mean, the continuous implicit surface might have some issues, especially in the very sharp corners. It will probably will, well, I know it will run them up a bit. But specifically the continuous, the implicit surface formulation, it's not that it kind of it makes smooth the field, but not exactly the surface, right? Like when you do the post-processing, which is the marching cubes to recover the surface, because that's done numerically, you can still get the sharp differentiation between in the edges. I don't know if it's clear. It's it's in the transition from the surface to the free space where it's smooth, but once you do the magic cube, it becomes sharp because you discretize at that stage.
Okay, thank you.
So no more questions?
Maybe another question is, how do you think about recently, like a very popular Gaussian splatting?
Yeah, that's a great question, and I usually get these questions because people is always interested of why we are doing Gaussian processes and now deep learning. So it's all the approaches I presented here. I mean, for the reconstruction and the distance field mapping are with depth sensors. So we are not using the images. So to me, the Gaussian splatting in particular, but also it could be the nerves are complementary, right? So once we have once we recover the mesh, that in our cases, it looks, it's a color mesh because we associate color to our mesh, but that's the only thing that we use the color for. So if combining our meshes or our distance field with Gaussian splatting, I think it's complementary. That's something we started to explore with Lan and Fred. But I mean, we haven't done much, but that's an idea that we want to pursue.
Okay, thank you.
Hopefully the people who are not in robotics kind of got some of the gist of the work. Awesome. All right. Thank you very much, everyone.